Okay, Mr. Samuels here with a quick lesson on electron configuration. So to review, orbitals are the regions of space that electrons can occupy in the atom. They're not nice, neat little circles like Bohr thought, but strange regions where we have a probability of finding them, as was discovered by Erwin Schrödinger. So there are four types of orbitals the electrons can occupy, and each one has different energy levels. So here are some examples. So there's the 1s orbital. You can see this one here has just a simple sphere kind of shape. That's where 2 electrons are allowed to be. And then electrons could occupy this other 2p orbital. It's a little different shape. The electron could be here or here, but not in between. As we go to higher energy levels, the shapes get more and more complex. But just understand that there's also a 2s orbital that's a higher energy but looks the same shape as this. There's a 3p orbital that's higher energy but the same similar shape as this as well. That's the main things you want to keep in mind. Okay, so most important thing to write the electron configuration showing where the electrons are in the atom is something called the Aufbau principle. The Aufbau principle states that an electron occupies the lowest energy orbital that can receive it. So, the book has this crazy setup for how to find out, which electrons are where, and I don't recommend it. Just get this basic idea that when you're filling a glass of water, you got to fill the bottom before you fill higher up. Okay, if you try to fill higher up, it'll just fall back down to the bottom. So, what is the order? Well, first off, you have to know the maximum number of electrons each orbital can have. All right, so you got S, P, D, and F. S's hold 2, P's hold 6, D's can hold up to 10, and F can hold up to 14. So there are 7 energy levels, and I didn't even bother writing it with here because by the time you get to 7D, we're looking at over 100 electrons, and that's just not really any point in looking at those because no atoms have that many. So let's go through the order here. Now, the first lowest energy orbital, every electron has to start by filling this 1s orbital. If you have a hydrogen atom with just 1 electron, it's going to fill that one first. Now, after that, we go to 2s. Okay, that's the next highest one, so you can put 2 in there because it can hold 2. Then 2 in here. All right, then if you got 2 there, got up to 4 now. Now we go to 2p. 2p is the next orbital, and next higher energy orbital, I should say. That can hold 6. Once that's full, then we move to 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 6f, yeah, exactly. So you don't have to memorize that order as long as you can build this chart, okay? SPDF, that's all you got to remember. Smart people do fine. Then start with 2 for S's, S's hold 2, and then just add 4. 2 plus 4 is 6, P's can hold up to 6, D's can hold up to 10, etc. So I'm going to come back here later just to show you guys why this chart is so useful when it comes to an example problem, but the most important thing is just to understand how to read it. Don't just read it like a book, because if you go through left to right, that'll work great until you get here. After 3p is not 3d. You've got to follow the arrow. See the point here? It's going down and left. Go down the slide. Whee! There you are, 4s. So after 3p, the next highest energy is 4s, then 3d, then 4p, then 5s. Ask yourself, do you know what comes after 5s? You should be saying 4d. Hey, you're right. Yay. Okay, let's look at some examples. Lithium. So lithium has 3 electrons here. You could figure that out from the periodic table. I just gave it to you here to make it easy. And so which orbital does it fill first? Well, the first one there, 1s. After you fill that 1s orbital, you can put 2 in there. Then that next electron has to go to the next orbital, 2s. So you notice here we say 1s because that's the orbital, and this little exponent thing is just telling you how many electrons are in that orbital. So there are 2 electrons in the 1s orbital and 1 in the 2s orbital. Add them up and you get 3. Let's look at another example. It'll start to make more sense. Oxygen. So go back. We can put 2 in here. We can put 2 in here. We can put up to 6 in here. So 2 and 2 is 4. Add 6, that's going to be too many. We don't need that many electrons. We just need 8 for oxygen. So this last orbital doesn't have to be full. These ones all have to be full because that's that Aufbau principle. You got to fill up the bottom of the bottle before you move on. But this one doesn't have to be full, okay, because this is on top. This is the outermost energy level. And so if you add those up, 4 plus 2 plus 2 makes 8. Bada boom, bada bang. So I'd stop for a minute, try those, pause the video, and then you can check your answers. Yay, you got them all right. Yay, notice all of them are full except for the outermost one. The last one here does not have to be a full orbital, but the numbers always have to add up here, and any of these orbitals before have to be full before you move on. Okay, let's try some harder ones. Pause the video again, try these out. All right, you got them all right, didn't you? Yeah, of course you did, because you're amazing. Notice here, a lot of people get screwed up here. Between 3p and 3d, there's another orbital that has energy in between, more than 3p but less than 3d. If you go back and you ignore the arrows that we talked about before, then you're going to get in trouble. You tried to go from 3p to 3d, you silly student. You should have just written down the slide, whee, to 4s before you go up to the next one. All right, 3p, then 4s, then 3d, then 4p. Got it? Good. Okay, so now we're going to look at these. Yes, now notice this gets kind of long, and this is only 33 electrons. If I gave you something like gold, you'd be killing yourself. So I'm going to show you a shorter way to do this. This whole section here can be simplified in just that little noble gas in bracket. What it's saying is if you wrote out argon, it would look just like this. And so we're saying, hey, we know all that's going on. What's happening on the outside? Because these electrons are the ones that are going to be involved in bonding and other important things for the atom. So let's show this other way, kind of a shorthand version called noble gas notation. In noble gas notation, you start by writing the noble gas from the line above in brackets. So if you look at the periodic table to number 33, arsenic, you'll see if we go on the line above all the way to the right, the noble gas above that one is argon, Ar. We wrote that in brackets. Okay. Now, after that, we start from the s orbital on the period of the original element. So this trips up students sometimes. They're trying to look up argon. That's not the original element in question. The original element was arsenic. So we go and look at the periodic table. You guys can see that arsenic is on period 4. That's the number on the left. If you look, the periods are on the left. Okay, good. Yeah, fourth one down, fourth row. So once we put the noble gas above, argon in brackets, we start with 4s since arsenic is on the 4th period. Fill that one up. Now remember, argon already had 18 electrons. So to get to 33, we go 19, 20. After 4s, if you go back to that staircase, is 3d, those hold 10. So now we're at 30, and we only needed 3 more to get to 33. Bum, ba-da-bum. Okay, let's try some. Use noble gas notation. Pause the video for a moment, give these a shot. Okay, check your work. Let's see how you did. All right, well, make sure you start on the right level. If you put 2s, that means you looked up neon instead of magnesium. Make sure you're looking on the period of the original element to find this here. Make sure if you went past 3s, 2, then that probably means you forgot about the first 10 that were already covered by neon. And then we only needed 2 more to get to 12. All right. Moving on. You should be asking a very important question now. What the heck does this mean? Who cares? This is just a bunch of letters and numbers. It's fun once you figure it out, but it's actually useful. See, the ending of the electron configuration tells you something about the properties of those elements. For example, if you look at lithium and sodium, if we do their electron configurations, you'll see lithium ends in 2s1 and sodium ends in 3s1. That same ending means they have similar properties, so they're in the same Family, you got it, alkali metals. It's that one electron in the s orbital that gives them their behavior and explains why they do things like react violently with water. Also, this explains valence. Atoms gain or lose electrons to achieve a more stable electron configuration. So for example, if you do the electron configuration for fluorine, you'll see that it ends in a p5. Now, that partially filled p orbital is not as stable as a filled p orbital like neon. So it wants to gain an electron, so it can end in p6. And that's a more stable configuration. This explains why fluorine has a valence of -1. Similarly, lithium and sodium want to lose that S1 electron so they can have a filled outermost orbital. If sodium loses that one now, its electron configuration is going to end in 2p6, just like neon. And what that does is that gives it a stable electron configuration and a positive charge, Na+. That's why sodium has a valence of +1.